is this. One, find a polynomial that is monic, has coefficients in the right field. The one that you're interested in this case, the field is Q, has coefficients in the right field and alpha as a root. 2, prove that it is the smallest possible degree, that is of the smallest possible degree. For example, by proving it's irreducible. So let's see this applied to these other examples that we had. Example 2, it was about cube root of 2, and again I claimed that we were actually spot on. That is, x cubed minus 2 is the minimal polynomial. Okay, I certainly know that the minimal polynomial of cube root of 2 over q could not be degree 1 because cube root of 2 is not rational. That again follows from the fact that 2 is cube free. However, I don't know right away that the minimal polynomial of cube root of 2 could not be quadratic. Yes, x squared minus 2 does not work. It does not have cube root of 2 as a root, but there could possibly be some other monic polynomial with rational coefficients, x squared plus ax plus b, that might have this one as a root. How do I exclude that possibility? So this is where the corollary comes in useful, because if I could just show that this is irreducible over q, then I know it's the minimal polynomial. And in fact, it is irreducible because x cubed minus 3 has no roots in q, so it's irreducible. You could also use the Eisenstein criterion with the prime 2 to conclude that this is an irreducible polynomial. So the corollary tells me that if I found a monic polynomial with rational coefficients that has cube root of 2 as a root, and the polynomial is irreducible over q, then it is automatically the minimal polynomial. Let's move on to the next example, which I think was zeta 5. And the polynomial we found for zeta 5 was x to the 5 minus 1. But I claim this is not the minimal polynomial. Of zeta 5 over q. Why not? Because you can find a polynomial of smaller degree that zeta 5 satisfies. Namely, note that this polynomial factors as x minus 1 times x to the 4th plus x cubed plus x squared plus x plus 1. And zeta to the 5 is a root of this polynomial, not of that, right? Zeta to the 5 is cosine 2 pi over 5 plus I sine 2 pi over 5, so it's not equal to 1, so it's not a root of x minus 1. So it must be a root of this polynomial. So zeta 5 is a root of this polynomial. How do I know that this is the minimal polynomial of zeta 5? It is monic, it has coefficients in q, but how do I know this of the smallest possible degree? Well, if I could only show that it's irreducible over q, then I would know it's the minimal polynomial. Do I know that it's irreducible over q? Well, that was one of the last things we proved in the video about irreducibility, where we said that if there is a prime p such that my polynomial like that starts with x to the p minus 1 and then x to the p minus 2 and so on, then such a polynomial is irreducible over Q. These are the so-called cyclotomic polynomials. And you see when I take the prime p equal 5, that's actually x to the p minus 1 plus x to the p minus 2 and so on. So, and x to the 4th plus x cubed plus x squared plus x plus 1 is of the form x to the p minus 1 plus dot 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 plus x plus 1 for prime p equal 5. So is irreducible over Q. So this is the minimal polynomial of zeta 5 over 3. What about the other examples? So example number 4 was radical 2 plus 3, and we found this polynomial x squared minus 6 plus 7, and I claim this is the minimal polynomial of radical 2 plus 3 over Q. I recommend that you pause the video now and try to argue for yourself why this is the minimal polynomial. Okay, let's now do this together. Why is it the minimal polynomial of this element? I note that this element couldn't possibly satisfy a polynomial of degree 1 because it's not an element of Q. So as radical 2 plus 3 does not belong to Q, the degree of minimal polynomial is not 1. Why isn't it an element of Q? Because Q is a field. If this is an element of Q, I know minus 3 is also, so this plus minus 3 would also be an element of Q, which would mean radical 2 is an element of Q, but radical 2 is not rational because 2 is square free. So the degree cannot be equal to 1, so it must be at least 2. And this is a degree 2 polynomial that radical 2 plus 3 satisfies. So it must be the minimal polynomial. However, you note, right, by the example here, by example 3, that the sort of quote obvious choice is not always the minimal polynomial. If I asked you about zeta 5, to me x to the 5 minus 1 is sort of the obvious choice for the polynomial that zeta 5 satisfies. After all, by definition, it's the fifth root of unity. However, it turns out that it's not the minimal polynomial. Sometimes there are polynomials of smaller degree, so you have to be careful. In particular, in the last example that we had, the last example was radical 2 plus 1, radical 2 plus I. And so the question is the polynomial that we found, which was x to the 4th minus 2x plus 2x squared plus 9, is this the minimal polynomial of radical 2 plus I over Q? Let's see, I know that radical 2 plus I is not an element of Q, so the minimal polynomial must be of degree at least 2. However, this guy here is of degree 4, so it's not immediately clear that it is the minimal polynomial. One way to show that it's the minimal polynomial would be to show that it's irreducible. To do this, you need to find all the roots and show that none of the roots live in Q. And secondly, because it's a degree 4 polynomial, you need to show that it doesn't factor as a product of two quadratics. I encourage you to try and do it. I'm not going to do it here on the board because soon we're going to learn a somewhat better way of actually proving that this is the minimal polynomial of radical 2 plus I when we develop more tools that deal with field extensions.